Okay, so good night, everyone. After some technical difficulties, I will now go back through question three as a demonstration and continue on from where we left off last week with flowcharts. I'll demonstrate this question again, and then I will let the students, you all, work on the rest of the questions. And maybe we may start out the problem solving process if there's enough time. All right, so this is the algorithm for question three. The question was whether the was to create an algorithm that would take in a number and then print it out if it is a prime number. So starting off, I have an oval for the start. And then here I have a square where I declare all of my variables. The I variable, num is prime, and limit as integer. Then next, as a parallelogram, I have insert a number. And then right after that, I have another parallelogram saying that I'm going to read num as according to here. So after this has been printed out, it will take in a value for num. Then once that value is taken in, I is then assigned the value of 2 to then go into the for loop, which is on the next slide, where I have a diamond here to represent the condition. So as long as I is less than the limit, which as explained before, in a for loop, the I will increment or increase by 1 through each loop until it gets to being equals to the limit. So when it is equal to the limit, it would then break out of that loop. So it can be represented as a condition using this diamond. So I started off with the true line. So while this is true, it'll then test another condition in an if statement, whether if num mod I is equals to 0, which is if num when divided by I is exactly divisible with no remainder. So if it is true, the flag variable that I have here would be stored the value of 0, meaning that it is not a prime value. And if it isn't divisible exactly by I, then it'll be given the value, then its prime will be given the value of 1, meaning that it is prime. So then when it exits this condition, it'll come back out here into this for loop, testing I again. But I should really, for the sake of demonstration, I would just put here I is equals to I plus 1, just so that you see that when it comes, oh, this condition here, I will be incremented. It'll be incremented and then we'll come back up to this condition here and test again whether if I is less than the limit. Oh wait, I forgot to write the limit line. Okay, so I will just briefly go back and put a line here just to assign limit to the square root of num. The reason for using the square root is because once you get to the square root of a number, there are likely no more factors that can divide that number. There are likely no more prime factors that can possibly divide that number. So I'll just use the function square root num. Put it in here and then come back and rejoin this. All right, so coming back out here to do the false line. So if I then becomes equal to or greater than limit, which I said just now is going to be square root of num, it'll then continue on with the program after this for loop, and then it will test again with another if statement whether is prime is equals to 0. So this if will be just testing the variables that we would have inputted into over here that would have been flagging whether the number is prime or if it isn't prime. So then coming down here with true, then it will print out that num is not a prime number. And if it is not true, meaning if its prime is 1, then it will print out that num is not a prime number. And then we will just join up these two since they are going to be going to the same. And so after this is executed, then the program will end. So I'll just put the stop here. And while I label these lines here, are there any questions? No questions from Samara. I see Anwar has just left, so may have joined back, might have technical difficulties. So when I finish label here, we can go and work on question 4. Samar, do you still have access to this Jamboard, or should I share it back in chat? Okay, so can you work on question 4? I'll put it in the meanwhile, I'll give you some slides that you can work on, and I'll place the question here on screen while you get back on to the Jamboard. So let me know when you are on the Jamboard. Okay, so the Jamboard is yours. You can now work on question 4, and I'll give my feedback at the end. You can also ask questions anytime if you need to. No problem. I'll send it now. Copy link. Sending in chat now. All right, so I see that you finished the algorithm. So let me just check it out. So here the definition, we define total, num, and I as integer should be rectangles since they are process steps and not input output. So I'll just, okay, now you get it. So here I'll just correct this. Same for the average step where you define it as a float, that should also be a rectangle. This one is right. This one is right. But here you should have a for loop. Because I think you forgot the for loop part. But I'll just write it in down here. Let me see, where can I put it? Because everything else here does seem to be right, just except the for loop part. So I'll just, okay, so just to show you, I'll just, I'll probably stick it up in here. Right, so I'll just put it up here. So in this situation, I would just put while I is less than 5 since it's going up to 5. So I'll route this from here to up here, come down, go in, and once it is true, it will read down into here where you'll read num with parallelogram. That's right. Right. Total as square. You iterate here, square again, correct. And then I'll bring this down here as it is not going to execute everything back in this loop to see if it is still less than 5. And then as my quote unquote false line, I'll just put it up here. This probably looks confusing, but I'll just label it so that you can actually try to make it out. So this is if it is true here, and if it is false. And then these would be just your flow lines right here. So coming back down, you then have average would be total divided by 5 as a process block. And then you have your 2 print statements here as parallelograms and then your stop. So other than missing out the for loop, you have everything here correct. So I will stop this meet again and then, okay, understand now? All right, so do you want me to do another flowchart example, or do you want me to go into the problem solving process? Okay, one more. All right, so I'll stop this meet for a short while, and then we can rejoin. So we can go through one more flowchart and then start on the problem solving process. All right. Okay, cool. So let me just end this meet quickly and then restart. Okay, so let's just start back where we left off. So we will do question 4, and then we will go into the problem solving process. All right, so I'll give you some slides to work on. And then I will put this question, the algorithm here on the slide for you to work on. So if you have any more questions, then you can let me know. All right, so I'll just put this here. And Samara, you can work on it like the last one. All right, so you're finished? Okay, so this looks mostly right. All right, so you do have to define total and num as integer. In this rectangle, you have total as a rectangle, the output, the print as a parallelogram, and then you do have the condition diamond here. So while num is greater than zero, it'll then read in num and then work out the sum. The only problem that I see here is that you should have run this back up here when it retests the statement. Because technically this is still a loop. So it'll keep running until num is either equal to or less than zero, which then here you have as your null condition. It'll print out total and then stop. But other than that, the flowchart looks correct. So you understand where you went wrong here? All right, cool. So just remember that when you have a loop, you have to, unless the, well, as long as you have a loop, at least one of the branches, usually the yes branch, should have to come back just above the diamond itself, like around here, for when the test has to be redone. So just remember to put a flow line back up here for when the test is reconducted. And then, but you can just keep your null or your false line separate, continue off the program. Understand? All right, so do you still want me to go on to problem solving, or do you want to do another one? Okay, so going on to problem solving. Let me switch my screen now. All right, so in this lesson, we'll now discuss the problem solving process. Okay, so the whole purpose of computers, their reason to be, or the reason why it's been created, is to solve problems. Like, so therefore, at the heart of all of its operations, it is to solve problems, to produce a desired output given an input, and then try to work its way towards that desired output. So these computers are designed to solve problems for users in a finite set of clear unambiguous steps as given by the programmer. However, before any of the program can be written, the problem-solving process must first be undertaken. Okay, so the problem-solving process has 5 steps, but the fourth step can be divided into 2 steps. But according to the syllabus, it is 1 step. So the first step is to identify and define the problem. Then the next step is to analyze the problem. The third step is to generate possible solutions. The next steps will be to develop the best solution into an algorithm and test that algorithm for correctness. And then the final step would be to implement the solution and review it. Okay, so for the first step, which is identify and define the problem, this involves recognizing the problem and describing it explicitly. Here you see what exactly is the problem we're trying to solve in all its detail to ensure that you know what is to be solved and could discern possible points that you can solve the problem from. Next, analyzing the problem. This involves examining the problem in great detail in terms of its input, its output, and its processing steps that are required to produce the output that's desired. The program may also be split or broken down into smaller subtasks or mini sub-goals in order to simplify it and make it easier to solve. As opposed to a large complex program, it might be easier to break that down into smaller steps and then work on those small steps in order to, and then bring them all together to make the complete solution. Next is defining, well, this is still under analyzing the problem, but a defining diagram or an IPO diagram, ignore the trace table part. That is for later. A defining diagram or an IPO diagram may be used to model what set inputs would be, the processing to be done, and the desired output. So here you can see an example on here. So here you have your inputs, which would be your grades 1, grade 2, and grade 3. Then in the process block, it would then show sum all the grades and then divide that sum by the number of grades. And then here for output, it would then have the student's grade average. So here you have your inputs, your process, and your outputs, your IPO. The next step would be to generate your possible solutions. This involves producing all the possible solutions to the defined problem. Every potential solution should be considered at this stage, and none should be discarded. New potential solutions could also be created by bringing together or borrowing and merging ideas from other potential solutions. And all of this is to find the most effective, concise, and efficient solution to the problem, which would then be the best solution. So when you have found this best solution, you would then have to go to the next step, which is to develop it into an algorithm. This algorithm may be represented by either a flowchart or a pseudocode algorithm. And when you are testing this algorithm, a trace table should be utilized to identify and correct logical errors found in the program. A trace table is a diagram which allows you to see the state of an algorithm at each step of it. So here is an example. The picture might be a bit blurry, but I'll just point to it. So here is an example program on the side. So these here would be your variables, and then this would be your output. So depending on what is inputted or what is processed, values would then be entered here, and then at each point when it is changed, they'll all be written in here. And then when it gets to the point of output, it'll then print out what is at that particular moment being worked out to be, in this case, the lowest number and the highest number. So the trace table is mostly used for working out the program and to see whether mathematically or process-wise it actually does what it is supposed to do. And then for the sixth and final step, after a flawless algorithm has been generated, the solution may be now entered into a computer where it can become useful. The algorithm is first translated into the specified programming language, which in this course would be the C language. The source code is then compiled and ran, and the program, now fit to solve its initial problem, must be reviewed and maintained. This involves updating the source code to address any problems that may arise, or if new functionalities need to be added to the program, or if a functionality has since become outdated and thus needs to be updated. So this would then tie the final step of this process into the first step, making it a cycle. So when you finish code a program, the program is never completely done. At some point, at the professional level, you're always going to have to be revising and reviewing and maintaining your program because bugs will inevitably come up, and then these bugs become new problems that would then need to be solved. In addition, at the commercial level, there may be regulatory issues that may require you to change certain functions or add or remove some. So that then becomes a new problem that you'll have to solve. In addition, you may also, if you are creating a program for a company, then, and if they want a new feature to be added on, that then becomes a new problem that you will have to work through the problem solving process to work out. So the review part is It's the most important. Well, when you are done the program, review is what keeps the program cycle going. So when you keep reviewing and maintaining the program, you will keep going through the same process over and over as you have more problems to be solved. All right, so are there any questions on this part of the problem solving process? All right, no questions. So I'll just briefly go into the theory behind algorithms after we've been doing more of the practical side. So I'll just go through very briefly what the theory behind algorithms are. Right, so an algorithm is a sequence of instructions written to solve a problem in a finite number of unambiguous steps. Algorithms play a large role in the problem-solving process as they provide a clear-cut way by which the problem can be solved. Also, the use of algorithms in the process is beneficial to a programmer as algorithms don't follow the syntax of any particular programming language. This means that any algorithm that you devise is universal. So the pseudocode algorithms you've written, the flowcharts, can be understood by any programmer and could be translated into any programming language. So the algorithms that we went through earlier, someone can take that same program, write it in, let's say, C++, and someone else can take that same program and write it in Python or Java, and then it should all come out to the same result. Well, even if you take into account the specific differences between the language, because at its heart, the algorithm is the steps that the programmer will and the computer itself would have to undergo in order for the problem to be solved. And these constructs that are within algorithms are universal to every programming language. So we'll now have the 4 characteristics of algorithms, which is a general solution to a problem, which, as said just now, meaning that it is universal. It shouldn't be specific to the problem, and it shouldn't also be specific to a programming language. It should be used that if you ever need to, let's say, add 2 numbers, it should be able to add any 2 numbers and not just, let's say, 3 and 5. It should be able to add all numbers that it can potentially come across. Number 2, it has clearly defined and unambiguous steps. This is because, well, despite people saying that computers are quote unquote smart, they aren't necessarily smart. They can't infer what we mean from what we have written down like humans can. In order to execute anything, the computer needs to be clearly told what it needs to do. So therefore, the algorithm has to be clearly defined and unambiguous in order so that we can tell the computer what exactly is supposed to be done to solve the problem. Number 3, it has a finite number of steps. Well, this is a given because, well, a program has a beginning and it has an end. A program shouldn't necessarily be going on forever. So it should at least have a finite number of steps so that when you are going through the program, it at least ends. And to expand on this point, that finite number of steps should also be efficient. So it shouldn't be like a bunch of what is called spaghetti code or code that is just jumbled up. A lot of code that is just meant to do nothing and adds nothing to the program. It should just include the most essential code that is necessary to solve the program, and anything else to format it or style it afterwards. But the algorithm should have what is necessary to efficiently carry out the program and solve the problem with as little steps as possible. And finally, there is flow of control from one process to another, meaning that in the program, it does have a sequence. It goes from one step to another. So after you print out a value, it should then either print out something else or process something or read in a value. So there should be a flow of control from one process to another. It should be a sequence. All right, so are there any questions on algorithms, meaning the theory behind algorithms? All right, so you're good. You're good so far. All right, so next week, we'll revisit the rest of the algorithm questions that we did previously, but this time we will apply the problem solving process and its related tools like trace tables and IPO diagrams in order to solve these problems. So are there any more questions regarding class in general, or is everyone good? Are no questions? You'll do more flowchart loop practice over the week. Okay, great. So if there are no more questions, then we can dismiss here. All right, have a good night and no problem. Stay safe.